All right. As you can see, the most important in electrochemistry, okay, is the types of methods. Okay, so most of the time in biosensors, okay, we focus on voltammetry. Okay, there are a lot of advantages using voltammetry. So if you remember galvanic cell, which you have learned before probably. Okay. Galvanic cell versus electrolytic cell, yeah. Electro, okay, electrolytic cell. So this is the one that probably you have learned before during probably during bachelor's or I don't know. Galvanic cell versus electrolytic cell. So if we are talking about voltammetry, we are talking about electrolytic cell. Yeah, electrolysis, electrolytic cell. So why? Because we need to supply potential, yeah, in order for the reaction to happen. So that is the difference, biggest difference between galvanic cell versus electrolytic. If you remember that for galvanic cell, when you mix together two chemical reagents, probably two metals solution, metal ion solution, then the reaction happens spontaneously. So the easiest example of galvanic cell is pH meter. Okay, so when you dip the electrode or the probe inside the pH inside the solution, then you will get the reading of pH. So that is example of galvanic cell, meaning that actually you not the potential, okay, that is happening, the potential difference that is happening when you dip the probe or the pH uh, electrode into the solution, it, it happens spontaneously. Okay, it happens spontaneously. But of course, it requires minimum electric for you to read on the display. Okay, so I'm sure that you are, I think all of us are very familiar with pH electrode. Yeah, you just dip it and you get the pH reading. So the pH reading is actually based on the potential reading. So by now, I hope that you have done your homework and know what is potential. Okay, right. So uh, I'm not going to focus on the galvanic cell. Okay, so what I'm going to focus on is voltammetry. Okay, and it is if related to electrode. Oh, sorry, I don't know what happened to my okay, just a moment here. Okay, okay, all right. Just a moment. All right. So it's electrolytic cell. I don't know what terms that you learned before. Okay, so it's an electrochemical method in which information about an analyte is obtained by measuring current, yeah, as a function of applied potential. So by now you have read about potential, you have understand a bit on current. Okay, so this is voltammetry. Okay, in order for you to obtain information of the analytes, okay, we have to supply potential to the system. Okay, so this is potential stat. The potential has to be supplied, and we can observe current. Okay, once the reaction, the chemical reaction happen. Okay, so I don't really want to explain or go detail on the principle or theory of electrochemistry, because this is not electrochemistry subject, but you need to understand the basis. That's all. You need to understand the basis. Okay, as we go through, at least you will understand what is happening on the surface of electrode. Okay, so the keywords are voltammetry is an electrochemical method. Only one of, because there's a lot of electrochemical method, which information means that the information means quantitative, qualitative of the analytes that we are interested in is obtained by measuring current. Okay, and it has to be supplied the system. The reaction will only happen if we supply certain range of potential. So when potential is supplied, reaction happen, current will be generated. And from the current, we can identify probably quantitative or qualitative information of the analyte. So that is the basis. So now we look at the instrumentation. Okay, it's a three electrode system. Okay, basically we have working electrode. Okay, and this is the most important. This is where the reaction happen. This is where the reaction happen. And we have a potential to control potential as baseline. We have what we call as reference electrode. And the last is counter electrode, is to complete the circuit. Okay, yeah, because it's electrical circuit, it has to be completed. Okay, so these are the functions of the three electrode. Okay, that works in voltammetry. Okay, that is used in voltammetry technique. And for electrochemistry, most electrochemical method, they requires electrolyte. For most, there are some, probably you can use solid electrolyte, but for most electrochemical methods, they work only in wet condition. Yeah, they requires supporting electrolyte. That is the most important in voltammetry. The three electrodes working, reference, counter, and the condition with supporting electrolyte. Okay. Now, this is a bit of fundamental. So when we supply potential, okay, this is we can imagine that potential is a force. Yeah, it's a force given so that the reaction happen. So we have to force the reaction to happen. So we need to know the potential range. Yeah. Okay, we need to set the potential. I will show you in other slides how potentials, how the machines look like. We have to give a correct range of potential, because different reagents, different chemical reaction will only occur at different range of potential. So if we supply not enough potential, then the chemical reaction will not happen. So this is most important to study first. We need to know the potential range to be supplied before the reaction can happen. Okay. Now, once the reaction happen, then we can start to observe the current generated, because the reaction here will have the electron uh, from cathode to anode. Okay, then you get reduction, oxidation, which I asked you to read. What is oxidation? What is reduction? Okay, even though it's basic, probably you have forgotten about the meaning of oxidation, the meaning of reduction. So that's why I asked you to read last week. Okay, so from that reduction and oxidation process, there is transfer of electron. Okay, so transfer of electron generated current. Okay, it will generate current. Okay, so you can see that voltammetry measure current as a change in potential. So this is related. Certain range of potential, then you get certain amount of current. Okay, all right. So I don't want to discuss potentiometry. I just want to discuss voltammetry. Okay, because I don't think I'm capable to detail out all other than voltammetry, because this is the most important and the most being used in construction of sensor. Now, a bit on theory. Okay, so as I mentioned just now, it is not important for you to memorize all these, but at least you need to understand before we can move to understand electrochemical based biosensor or chemical sensor. If we don't understand the basis a bit, then it's difficult for discussion purposes. Okay, so this is what we call as Nernst equation. Okay, if you take a physical chemistry, you probably has come across this equation. Okay, Nernst equation, where you calculate the cell potential. Okay, so this is Nernst equation. You can see this is referring to the working electrode. Okay, and this is what we call as standard potential. What is standard potential? I hope that you have at least understood them during your reading along this week. Okay, because reduction and oxidation of most ions or element in the, not all, so I can't say how many in the periodic table is already listed, the value of standard potential. Okay, and then from this equation we can put the effect of concentration. Yeah, so this is the most important. There are many other equations. Okay, so this is one of the equation. Yeah? Nernst equation. All right. So now if we look at what happened, yeah, you can see that from here, okay, the example of the analyte is, let's say, ferrum 3 plus. Okay, ferrum 3 plus. So you can see the reaction is reduction or oxidation. Anyone?
Reduction.
Yes, very good. Yeah. So this is reduction of ferrum 3 plus to ferrum 2 plus. Okay. So what happened is, this is before we supply potential. Before, right? You can see the concentration is constant for ferrum 2 plus because there is no reaction whatsoever. So now you start to apply potential, okay? And this reaction happen. the ferrum 3 plus is reduced to ferrum 2 plus, means that now you have two types of compound, all right, ions, okay, right? Ferrum 2 plus might be increasing and ferrum 3 plus decreasing. So this is, you can see that the bulk concentration with regards to distance from electrode also is the concentration, the lower the concentration, sorry, the concentration, the higher the concentration, the bulk concentration, the what you call the farther far from the electrode, you can see the bulk concentration decrease. Why? Because you can for electrochemistry, it is very sensitive towards distance. Yeah. So we are talking about the one that close to electrode surface, okay, will be reduced. Okay, the one that is far from electrode surface will have problems, will have difficulty to be reduced. Okay, so you can see that the bulk concentration here that is far from the electrode is still very high, but those who are closer to electrode, it starts to decrease because now it has been converted to reduced to ferrum 2 plus. So this is what happened on the surface of electrode. Okay, we have to think about that the ions are moving here and there. Okay, and then to usually what we need to do is we need to stir the solution because the ions need to move. Okay, so there are three transport mechanisms: migration, where ions move through solution by electrostatic attraction. Okay, so ions is positive probably, and the electrode is charged. Okay, so depends on the charges, the ions will migrate. Convection, mechanical motion, means that you stir the solution, then the ions also will move. And the third one is diffusion. Diffusion, because just now we look at the bulk concentration is no longer constant. So the concentration here farther from the electrode is higher compared to the bulk concentration near to the electrode. So when there is a gradient, concentration different, so that also trigger movement of ions. So these are the three transport mechanism of ions. Yeah. So we cannot see it because it's something that we don't see, but this has been studied, how the ions, yeah, inside the, well, let's say it's inside the beaker, move towards the electrode. Now, so let's look example. Imagine this is the beaker. And then we have, in here, we have plumbum chloride. Okay. And this is the electrode potential. Sorry, this is the electrode potential for reduction of plumbum, okay, ions to plumbum. And this is the reduction potential for potassium, reduction of potassium to potassium in elemental form. So electroactive species in the sample solution are drawn towards the working electrode. So let's look at working electrode. So here is the working electrode. Another corresponding half cell reaction will also take place at the counter electrode to complete the electron flow. The resultant current flowing through the electrochemical cell reflects the activity. So this is the basics, yeah. that we can start giving in potential so that one of these chemicals will be reduced. So I think you remember that the more negative or the more positive will be reduced first or will be oxidized. Okay, I do remember that. You have to read back. Okay, the value of reduction potential will determine which ions will be reduced first. Okay, right. So let's look what happened. It should be moving. Okay. You can see that concentration gradient created between the surrounding of the electrode and the bulk solution. So this is the surrounding of electrodes, and this is what we call bulk solution. Okay. All right. So layers of K plus build up around the electrode stop the migration of Pb2 plus via Coulombic attraction. What does it mean? Now we have two ions, so competing for the surface of electrode. Depends on the reduction potential, which one will be reduced first. So once they are probably potassium, yeah, plus has covered this area, we can see that plumbum 2 plus no longer can go here because of the electrostatic charges, because both of them are positive in charge. So they have difficulty, plumbum 2 plus probably have difficulty to approach the uh, electrode. Yeah? Concentration gradient created between the surrounding of electrode and the bulk solution. So what's next after this? So it only can diffuse. Remember what is diffuse? Let's look at what is diffuse. Diffuse motion of species caused by concentration gradient. Yeah. So once there is a difference in terms of concentration, we start with K plus. Okay, so there is a difference in terms of concentration. So they can move. Concentration here is not just Pb2 plus, yeah, it also related to K plus as well. So what happened at electrode surface? Okay, we can do calculation by using Nernst equation. So again, I'm not going to teach detail of electrochemical related, but it is for you to understand the basis of how the analyte can be detected and the analyte can be quantified using electrochemical method. So this is the basis. Let's look at what happened. Is there any? All right. Let's move to, okay. There's another one that's, okay. Okay, let's look at detail, the reading. So this is what we call as voltammogram. If it is chromatography, it is called chromatogram. So this is voltammogram from, I think it's only 1G. Voltammogram from voltammetry technique. Okay, so let's look at if we have 0.01 molar cadmium, okay, and the supporting electrolyte is potassium nitrate. Yeah, right. So now electrode, once we supply potential, so here, if you look at here, we start to give potential from probably negative 0.1, and then moving to minus 0.2. You can see there is no reaction yet, no reaction yet, no reduction yet. But after some points, after some potential, we can start to see the current. Eh? So now, probably cadmium, more cadmium around the electrode are being reduced. Yeah. Okay. So starting from here, cadmium 2 plus is already starting to be reduced on the surface of electrode. What do we have here? Okay. All right. What's the information just now? Okay. And then the current increase when more cadmium is being reduced. There is electron transfer. So the higher the concentration, in here is 0.01 molar. So the higher the concentration, the higher the current will go. So the current will determine the quantitative. Okay, how much current generated will give an impression of how high the concentration of the species that we are measuring. So now, if you look at here, it is sort of saturated. Yeah, it is sort of saturated. And this is what we call as, this is, what does it mean here? It means that cadmium 2 plus all has been converted to cadmium. So there is no more cadmium 2 plus left. Okay, so it should reach a plateau. Yeah, right? So this is the current that determine the concentration of the cadmium 2 plus, right? Now, what is E half potential? Okay, what half potential is if current represent the quantitative, the how much, so the E half, okay, ID, okay, the half potential represent the qualitative. It's not accurate. It's not accurate like GCMS. It's not accurate like HPLC, but it can give some indication. For example, okay, this is cadmium. This is half potential for cadmium. This is half potential for potassium. This is half potential for plumber, for example. It's not that accurate, but it can give some information. We know, okay, that cadmium will be reduced at this potential. And we know that, for example, magnesium will be reduced at this potential. So this is what I meant by qualitative. The potential, the half-wave potential is giving an information on the qualitative part. The quantitative is the current. Okay, right. So this is the how we say the E half is half-wave potential. And the ID here is the limiting current. Okay, why? Yeah, because it's related to concentration. It is limited due to the concentration of the species that involved in the electrochemical process. Okay, so that's enough for you to understand. At least this process is very important for you to understand. Okay, we supply potential, yes?
Sorry, doctor.
Yes.
Doctor, I have a question regarding this graph, doctor.
Yeah.
I do work with the colorimeter, doctor, with the same type of multogram. So the X reaction there, where just now you mentioned won't be a reaction, and then there when the potential energy reach, it will go up, and then it will be saturated. But sometime during my run, I have noticed the uh, period where there is no reaction is not in a positive, it will be in a negative, doctor. Why the negative things are there, doctor?
That depends on the species. Meaning that because the reaction, okay, if you are working with voltammogram, depends on what actually inside the voltammogram. I'm not so sure what happened again? Inside the, I don't know which technique are you using. Voltammogram, there's a lot of sub-techniques under voltammogram.
Okay.
So what techniques are you using?
Colorimetry.
Coloring. Or Coulomb, is it Coulomb? Or
Um,
not so sure.
not so sure, doctor.
I also not so sure about it. But yeah, for voltammetry, we can have, for example, what we call as differential pulse voltammetry. Yeah? Differential pulse voltammetry called DPV. Okay, the sharing is happening right now. Called DPV, where you can, okay, have the reaction to be whether you can decide to have oxidation reaction or reduction reaction to be analyzed. Yeah? It does not have to be uh, reduction always. It can be oxidation. Okay, and then what happened? Sometimes the reduction potential is not always positive.
Okay.
Yes, because reduction potential can be negative, can be positive. So it depends on the species. Okay, so I'm not sure what species are you working with,
I'm
but
working with the chlorine. Mm,
probably you can check the chlorine standard value
mhm.
of the reduction potential or the standard potential, and then check whether what is the
Diseases. Okay, doctor.
okay, so I don't know. Yeah, we do observe a negative as well. So it works in negative potential and also in positive potential.
Positive answer.
Yeah.
Doctor, one more question, doctor. Sorry. Doctor, when I also notice when there is a negative potential, the just now the value quantitatively the value is reducing. Is that normal, doctor? By
When
quantitative, when there is a negative reduction, so there is the quantitatively the value is reduced than normal.
quantitative means that the quantitative of the
The of
concentration.
the of the species of the element.
Yeah,
Mm.
because just now, because I'm using cadmium 2 plus just now, yeah, as the
Yep.
example, it will decrease because the cadmium 2 plus now is converted to cadmium element.
Mm.
So of course, the value of cadmium 2 plus will decrease, and the value of cadmium element will be increased. Okay. I'm trying to share the slide again. I don't know what happened with my. Okay, that's why you observe that I froze. All right. Let's look at try. I'm trying again. Okay. Why it doesn't want to share? Probably the internet is not good today. Okay. Right. So here, uh, let's look at the reaction back. It's very irritating. Okay. Let's wait. Okay, it's very slow. Okay. What do you see now?
Voltagrams picture, doctor.
Right? And yeah, the stop share, the sharing screen, right? Okay. Let me unshare this one. Seems that it's very slow. Okay, it goes back to here. Bear with me for a while. Let me unshare this one. Stop share. Okay, this is the one that we last discussed. Okay, so we can see that from the beginning, working electrode is not yet capable of reducing cadmium 2 plus. Why? Because the potential is not enough. Probably it's not zero. Okay, it is not zero because of the residual current. Why we have residual current? Because we also have other electroactive compound, which is supporting electrolytes and whatnot inside that beaker. So that gives some small residual current, but it's okay. I mean, we can just minus this as a baseline current. But once the potential of the cadmium 2 plus is achieved, then cadmium 2 plus will start to be reduced. So Pavitra, that depends on the species. It can happen at the negative side. In this case, because the reduction potential is positive, so it happens at the positive side. But I think it's negative, right? You can see it's negative, yeah? Yeah.
Yeah, the axis is negative, doctor.
Yeah, so it means that it is negative. That depends on the system that you're using. We can set the sometimes we work from negative positive or positive negative because it's reversible actually. And once the reduction happens, then the current start to build up, okay, until it achieves saturation, meaning that the cadmium now means that the original species now is finished, okay. All has been converted to cadmium elemental, right? Okay, so these are two very important parameters in voltammetry is half-wave potential and the limiting current. So limiting current will determine the quantitative part, okay, the concentration of the cadmium 2 plus, and the half-wave potential is qualitative limiting current. Okay, half-wave potential is the qualitative, meaning that it identify whether, okay, as I mentioned, it's not accurate, but it can be an indication of what species you have inside the beaker. Okay, you can see that we can have two or more species. So let's say you have a mixture of cadmium and probably arsenic inside the beaker, then we should be observing two different half-wave potentials. Depends if their half-wave potential has a big difference, then you can observe two different potentials. Yeah. And if we have, for example, here ferrum, ferrum 2 plus, ferrum 2 plus with different concentration, also different concentration results in different current, but same potential because they are the same species. So if you run it separately, yeah, I'm not talking about you have ferrum 2 plus concentration of 1 to -4, and then you can concurrently in the same beaker run 0.5. You run the voltammetry analysis separately. So we should be observing the same half-wave potential because they are the same species. But since the concentration of the ferrum, okay, is not the same. So you can see the one that is highest is 1 10 to -4 is higher than 0.5 10 to -4. Okay, so this is an indication how we work with half-wave potential and the limiting current. Okay, I'm not talking about this. Okay, but just I'm giving you an information that under voltammetry, there is what we call as amperometric. Okay, and the voltammetry itself has a few types, different methods, amperometrics. We have pulse voltammetry, the one that I mentioned just now, different pulse voltammetry, DPV, and we also have cyclic voltammetry. Okay, and they serve for different purpose. When we use cyclic voltammetry, when we use DPV, when we use amperometry. So these three, Ampro, pulse voltammetry, and circuit voltammetry are commonly used in biosensor development. Okay, these are the things, biosensor or chemical sensor development. So this is just to share with you some information, but I don't want to discuss this. Going back to the other slides. Okay. So this is how potential stat look. Yeah. This is the name of the machines that can generate potential. Yeah. Different brand has different look, of course. Okay. So you can see we can have a bulky one, and then we can also have a very bulky setup. Okay, where the three electrodes are set up in the supporting electrolyte. So this is what I mentioned about. It requires wet chemistry. It has to be in the solution, and this is where we run the voltammetry analysis just now. Okay, but I mean, voltammetry has become smaller. This is voltammetry. This is potential stat. Okay, and it can be analyzed using phone. Yeah, we can just use apps. Yeah? So instruments are getting smaller. Probably the accuracy or the sensitivity is not similar for both, but at least we have some portable. Okay, if we need to do some analysis on site, this is much better for us to use. And on the detail of the reference electrode, working electrode, okay, this is the basic one. Yeah, this is basic one. We no longer use, we do use this for basic study, but for development of sensor, the electrode now is much simpler, is smaller, is thinner, so it's no longer, the setup is no longer looks like this. But if we do fundamental study, we still use this, yeah. Counter electrode, as you can see, working electrode has the biggest one because this is where the reaction, the main reaction happen. And we also have the reference electrode. Okay, this is an example of what electrode looks like now. Okay, from this to this is now even smaller than this. This is the size of what should I? It's the size of memory card. Yeah, probably a bit bigger than memory card. Okay, all right, so you can see this is the working electrode area, and we have the counter electrode, and also we have the reference electrode. This is reference electrode. Usually it's AgCl, argentum chloride system, and this is where the connection happen. Right? If you look at here, this is where the connection connected to the potential stat, and this is the electrode connected to the small potential stat and analyzed in the apps. Okay, so now this is where we start to work with. All right. Okay, so the next slide will discuss on more on what is happening on the working electrode. So from here, you need to understand that there are two things, very important things, is potential. Okay, we have to decide on the correct potential range, and the current generated will be used for quantitative, means that you have to construct calibration plot or any other quantitative analysis. We are using the current generated. Okay, so I think we should take a break. If you have any questions, we are going to discuss another slide. just oops. Stop share. Okay. If you have any questions, right. So I hope that you at least understand the fundamental. Okay. At least understand the fundamental, because before we proceed to the next slide, which I have shared before. So coming back to this picture, okay, coming back to, where's the slideshow? Yeah. So coming back to this picture, it's very important to understand we are talking about this part, transducer. And this transducer transduce, meaning that it will give you the output from the interaction of the analytes with the receptors. Okay, we have discussed receptors. We have discussed about bioreceptors and a bit on chemical receptors. So once they interact, okay, we need to read the interaction. So the interaction is being transduced, or is actually being analyzed, giving you a readable signal by transducer. And the transducer that we are talking about right now is electrochemical based transducer. So after this, we are talking about optical transducer. Okay, so I hope that you know where we are right now. Okay, all right. So I think I have done a bit on electrochemistry, some introduction before we proceed to examples of electrochemical sensors. Yeah. So just to give you an idea that under in analytical methods, there's a lot of methods, and we are only focusing on voltammetry. There's a lot of methods. So yeah, we cannot cover all. Okay, so I only covered the one that I used, and the theory of electrochemistry is a bit difficult to really, unless you are interested, then you have to take an chemistry subject alone, not combining with any other application. Okay, so I've shown you this, right? Yeah. So we will go back to this after the break. All right? Okay.
Okay, Prof.
All right. See you at 8.
All right, Prof.
All right, welcome back, everybody. Internet is not really good tonight. I hope that you can see the slide. Yeah, ready? Can you see the slide?
Yes, Prof.
All right, thank you. Right, so this is just to remind you what is happening on the electrode surface. Okay. Right. Remember the ions here have to move to the surface of electrode in order to be oxidized or reduced. Yeah. So if it is in bulk solution, means that it is a bit far from the electrode, then the possibility of the electron transfer is low. Okay, so remember the three mechanism of transportation just now. The convection, the first is migration, convection, and then diffusion. Okay, so those three are the process of how the ions can move to the surface of electrode. Okay, and this process is very, very important to be controlled, because if we don't control this one, then the analysis will not be accurate. Okay, means that there is a possibility of the chemical reaction is not happening because of the distance from the electrode. So these are very important to be controlled. All right. So these are among the things that we really have to look for. Not look for, but we really have to study and characterize. Okay. Um, in order to have the best results. Okay. One is the mass transfer. Okay, we can do stirring, we can find support the best supporting electrolyte. Probably we need to study on different type of supporting electrolyte, because different supporting electrolyte means that different chemicals will behave differently. Okay, it has to suit the analytes that we are working with. Election transfer is actually electron transfer, not election. Okay. So electron transfer at the electrode surface, okay, we have to optimize. Okay, there are ways to increase the performance of electron transfer on the electrode surface. Okay, we will discuss in later part. And the chemical reaction as well, there might be homogeneous, heterogeneous. Okay, the surface reactions such as the adsorption, desorption. Okay, this one, they are also electrodeposition. Okay, possibility of deposition. So those are things that we have to study. So among the things that we usually do is to modify the surface of electrode. We don't just use the original electrode, original, why it's not moving? Okay. We don't just use the bare, what we call as bare electrode, yeah, but we do use modified electrode in order to get optimize electron transfer, okay, and also mass transfer. So we have to do some modification on the surface for the purpose of development of sensor. Okay.
Sorry,
So
doctor.
yeah.
Doctor, modification on electrode in what term, doctor?
Okay. This one I will discuss in later part. Okay. What kind of modification that we can do? Yeah. During
Okay,
the
doctor.
Okay, so we can see there are a few factors, especially those affecting the electrode surface. One is the material that we use. We always want to have a high surface area. So the question asked just now, how do we increase the surface area? So among the things that we do is we modify, we put on top of the electrode with nanomaterials, because we know that having nano size material will increase the surface area. And sometimes we do We modify with conducting polymers. We modify with especially nanoparticles that enhance the electron transfer, but we know the characteristic of the material that will enhance the current and also the electron transfer. So we need to know what kind of material that we can put during the process of modifying the electrode to increase this surface area, conductivity, all right? So these are very important factors to study. Surface condition also very important because let's say we have porosity, anything that can affect the electron transfer, then we can study the fundamentals, okay? This one is about stirring, the dynamic of the solution, how the mass transfer from here, we want the ions to quickly move to the surface of electrode. We want that to happen so that the reaction will be faster. Okay, how do we do this? Among the things that we do, of course, stirring. Apart from stirring, we have to find a suitable supporting electrolyte in terms of concentration, in terms of types of chemical reagents, because we know that we have different types of supporting electrolytes. And this one also very important, temperature, but it's unlikely in lab setup, we don't have pressure, control of pressure, but temperature, we can do that. And related to this also, we can also study the pH, yeah, right. Apart from that, definitely the the electrical parameters, the potential, there are other things like if we study differential pulse, there are certain other parameters like the pulse that we have to control. That depends on what kind of voltammetry technique that we are using, yeah. So these are all something that we have to do some experiment to optimize, yeah, to optimize in terms of types of electrolytes, the concentration of electrolytes, the potential, what kind of material that we want to modify the surface of electrode, and do we need to control the temperature? Do we need to control the pH? Those are parameters that we have to study in order to get a better reading. This one I have shown to you just now, so I just skip this. So this is something that we have looked before, right? During the DNA-based biosensor. Okay, so for those, I hope that you still remember that DNA-based biosensors, they are based on hybridization. So remember the DNA probe is the green one and the target DNA is the red one. So if the target match 100%, okay, so we are talking about a positive match, 100% match, positive match. Confirm the whatever the bacteria or the virus is a confirmed match with related to the DNA probe on top of the electrode. Yeah, and we have talked about the linker, the chemistry, how to link the DNA probe before, right? So we have done this. And the one that we need to discuss is how do we get the signal? So we know that DNA is non-conducting. DNA is non-conducting, especially because it's biological. So how do we make it conductive? How do we change a biological molecule into something conductive? So that's the other thing that we need to think about. Naturally, it is not really conductive, even though they have negative charges at the backbone of the DNA, but we need to increase that electrochemical properties in order to observe these changes, yeah? Remember that these changes must comply, for example, 100% match, 50% match, or mismatches to confirm. So from the signal, we can confirm whether we have 100% or the analyte is there that we are looking at. Okay, right. So what we are targeting in getting the biological material, for example, DNA, to be electrochemically active is we have to put a label. Yeah, we have to put a label to that DNA probe or to any other in the system. Okay, so how do we do that? We have to look at a few types of label. Okay, so here particularly I'm talking about DNA based. Yeah, I'm not. I don't talk about immuno. I don't talk about aptamer yet, but it's just DNA. So this is the behavior that related to DNA, and there are different electrochemically active compound that we can attach to DNA. So among the compound is in what we call as intercalator. Okay, right? This is the process, intercalation. But the compound, the electrochemically active compound is what we call as intercalator. Why? Because the process is it intercalates into the spaces of the amino acid here. So remember, this is the amino acid in the DNA structure, and this intercalate slide into the DNA structure. Okay, so remember, one is intercalator. The objective is to change the electrochemical properties of the DNA. That's the purpose. Okay, now we have a groove binder. Okay, so what is groove binder? This is the area. Okay, this is area where we call it as groove. This is also groove. Okay, intercalator in the middle, but this is what we call groove, and this is what we call groove. So this part is called minor groove binder, minor groove binding part, and this is major groove binding part. So there are some compounds that we call it groove binder. Okay, DNA groove binder. So when you mix it with the DNA, they can bind with this area, the groove binder, major groove binder, or the minor groove binder. So now we know intercalators and we now know groove binders. Okay, so let me show you example of intercalators and groove binders. Okay, so this is the example of intercalator. Most common is methylene blue. Okay, and this is the structure of methylene blue. So if we look at the structures of other intercalator, you can see that they tend to have benzene ring. Yeah, benzene ring. This is another intercalator, ferrocene, FND, yeah, in short, ferrocenyl naphthalene diamide. So it can behave as intercalator, and at the same time, they are electrochemically active, right? So methylene blue, okay, you can see the benzene structure, and also ferrocene compound. Okay, they are example of intercalator. So let's look at, we have the groove binder. Okay, what is the common groove binders? Okay, you can see that they have crescent shape. Yeah? This is the crescent crescent shape, right? So why they need the crescent shape? Because remember, it has to be bind with the groove. It has to bind with the groove. So the crescent shape actually helps to bind with the groove. Okay, all right. And there are other types of label. Okay, for example, we have metal complexes. Okay, so this is another types of label. apart from intercalator, apart from groove binders, we can also use metal complexes, because this, you can see, they also can bind to the intercalating area of the DNA, right? So they will become label. So the DNA now has become electrochemically active. Yeah. So this is another example of metal complexes. Just now is ruthenium complex. Yes, this is also another ruthenium complex, but different ligand. Yeah. Okay, so I have introduced you to 3 types: intercalator, groove binders, metal complexes. Okay, let's go to this later. And there is also a metal nanoparticle that we can use to label the DNA as well. So you can see it does not goes to the groove. It does not goes to the intercalator side, but it attached via chemical. Yeah, so we have to use certain linker, for example, biotin. Yeah. Yeah, I forgot about. I haven't shown you the streptavidin biotin interaction before. I forgot about it. So this is the interaction of biotin, biotinylated DNA, and streptavidin attached to metal nanoparticle. So you can see that biotin, and streptavidin, they have perfect match. It's a established chemistry. Okay. So we can label the DNA by using biotinylated DNA, and then we can react the biotinylated with streptavidin metal nanoparticle. Okay, so this is quite common chemistry. Biotin with streptavidin. You can Google it. Okay, so these are among the strategy that we can use so that DNA now becomes electrochemically active, right? So this is a step that we need to do first before we can develop DNA-based biosensors using electrochemical technique as the transducer. All right, now, right. So let's look at example. Okay, let's look at example. Okay, 1, 1, 2. Okay, this is, okay, this one is easier. So how do we introduce the label? Okay, so I think I have described to you this diagram before, that we need to do some modification. Okay, this is Pavitra, an example of modification on the surface of electrode. Depends on what is the purpose. So here, there are few modifications involved. On the surface of an electrode, we have silicon nanowires. These are and gold nanoparticles. Yeah. So in here, silicon nanowires and gold nanoparticles contribute to the increase of surface area and also conductivity that enhance the electron transfer. Okay, which is very important, because if we don't do that, then the signal, the current generated might be a bit too low. Okay, but with the enhancements of the electrode area, surface area, or conductivity, then we can get a better signal. And at the same time, the silicon nanowire, okay, I remember that we have discussed about how to modify the chemistry of silicon, remember, to attach a DNA. Okay, so this is another strategy using silicon, okay, to attach a DNA. In this case, there are combination of amine, and then you have thiol group. Okay, as long as you can manipulate the system. You know what will be at the end point. Okay, and then the DNA probe is also thiolated, and we know that thiol has very good affinity towards gold nanoparticle. So we actually use the silicon and the gold nanoparticle as enhancement of electron transfer, at the same time help us to link, the DNA probe on the surface of the electrode. Okay, so this is what we have talked about. The attachment of the receptors, in this case bioreceptors, to on top of the electrode. So this is DNA probe, and comes the target DNA, okay, from the sample, probably extracted from the sample. In this case, we are working with dengue biosensor. So the targeted DNA comes from the dengue virus. So when it moves here, the hybridization should occur. But again, as I mentioned, even though it hybridized, because it is non-conducting, DNA is non-conducting, we cannot get the signal. We cannot get the signal electrochemically, so we have to label it. Okay, so once they have hybridized, we can use different strategy before they hybridize, or in here we are using after hybridization. We incubate the whole system inside intercalator. So in this case, we are using methylene blue as the intercalator. So you can imagine, once they incubate, then they will intercalate into the DNA structure. Okay, so once that intercalation done, you can see the blue dots here. So the methylene blue intercalated into the DNA duplex, DNA structure. Then we can generate the signal, because now it is already electrochemically active. So we can observe the reading before and the reading after hybridization to confirm. Okay, so you can see that it might be before higher or after higher. It depends on the strategy. Okay, so I don't want to confuse you, but enough for you to know that after these steps, we have labeled the DNA into electrochemically active. So now we can do the signal. We can do the measurement using electrochemical technique, because now it is readable. It's not just by molecule. It is become electrochemically active biomolecule. Okay, so this is how electrochemical technique is being used in development of biosensor, DNA biosensor. Okay, so we need to use electrochemically active label. Now, another example, if I have, okay, this is supposed to be optical. I think I don't want to discuss this. Okay, is using the metal nanoparticle. Okay, so now this is the DNA. Sorry, this is the this is the capture probes. Okay, they have the capture probes, and they have a nanoparticle label detection probes, and they have target. We have 3 sets of DNA here. So we need to play around with the sequence of the DNA. So now you can see that once it is hybridized, okay, the target and the detection probe, okay, once it is hybridized, but the DNA probes here already have a metal nanoparticle as the electrochemically active label, right? So you can see that the reading that we got is actually from the metal nanoparticle. Okay, we have We are not detecting plumbum, cadmium, or zinc here, but we are confirming the hybridization process from the label, labeled by plumbum, labeled by cadmium, labeled by zinc. So this is what is happening, okay? The usage of metal nanoparticle as label for the hybridization. I know it's something new for you, but just at least you can get some understanding the fundamental. Okay. Now there are also techniques that we can use apart from labeling, yeah, because labeling can be difficult process. It requires time. Okay. It is called labelless electrochemical DNA biosensor. So there are different techniques. For example, what we call as EIS, yeah, electrical impedance technique. So this is the same principle. We have the DNA probe, okay, and then exposed to the target, and then we have hybridization. But so by using EIS, because it's a different principle from the voltammetry just now, we do not have oxidation reduction whatsoever. So this is what we can observe from EIS to confirm the hybridization. I would say that it is not really an accurate method because it is just based on impedance is based on, I'm not good in impedance, but you can see that they behave differently once the charges are different. Okay, they are they are based on the charges. So for this one is for this like metal nanoparticle label or intercalator label, they are more accurate compared to this EIS. But the EIS technique is actually very much being used right now. So I don't know why. Okay. Right. So just now is DNA and now is the immuno. How do we use electrochemical in development of immunosensor? So immuno is antibody, right? Okay. So same goes to like DNA, it has to be labeled because if it is just antibody, it is non-conducting. Okay. So we need to label. Okay. So how do we label it? Okay. Similar like DNA just now, but it does not have intercalator. It does not have groove binder because it does not have the shape of the DNA. So we can use a metal nanoparticle. You can attach, okay, let me go. Okay. So here is what we call as capture antibody. I hope that you can see. Okay, this is the capture. And then the purple one probably. This is the purple one. Okay. Is the analytes or the antigen or the virus or the bacteria that we want to detect. And we have discussed before, it will bind to the epitope of the antibody. Okay. And then we have another set of antibody in order to show a signal. Because if you have just, I cannot draw, my iPad is not functioning well today. I hope that you can imagine the Y shape of the antibody interacting with the antigen, but it cannot be, I mean, it will not generate signal because it's not conducting. So we need to have another set of antibody. You can see that this is another set of antibody. Okay, that is labeled. Okay, so here there are two labels, magnetic particle and enzyme. So enzyme can be electroconducting, and the magnetic also can be electroconducting material. Okay, So this is the process. The labeling requires works to be done. And in order to read the signal, we have to electroactively label the process. So in order to use electrochemical technique. Next one, okay, the same example. This is by using metal nanoparticle. Just now is enzyme. Okay, so by labeling with the second set of antibody, we can observe the peak for metal just now, and then this is the principle, means that that is how we confirm that this reaction do happen. Okay, all right. Okay, enzyme as well done. So common text, a common label that is being used for immunosensor, from my experience, is metal nanoparticle and enzyme. Okay, and this is also labelless, just like DNA just now. By using impedance, EIS, we can do the analysis of immunosensor, development of immunosensor without label. So we just use the technique of EIS. You can identify the interaction between antibody and antigen. Okay. So the last part will be APTA sensor, because those are the one that we discussed: DNA, antibody, and aptamer. So in APTA sensor, there's so many things that you can do in terms of strategy, but these are the label that you can use: metal nanoparticle, enzyme, as well as redox compound. It depends on what kind of uh, reaction you wish. It's difficult for me to explain because APTA, even though it's a series of amino acid, it's a series of nucleotide, it does not behave like DNA hybridization. No. Okay. So it is a folding. I think I have discussed about APTA, how aptamer works. It is folded, yeah. So folding oligonucleotide that react with the adelides. Okay, so now how do you tag the process? How do you label? You can label the aptamer itself, or you can do extra, like here we can do a combination of aptamer and DNA. Okay, I think I shouldn't be too detailed about this, okay? Unless you are doing research on this, then we can discuss more, okay? So this is example of aptamer, okay? And then you can expose it to electrochemically active. This is andalite. So this is how aptamer folded, okay? Interacting with the analytes, and by using another set of aptamer, which is labeled with enzyme. Okay, so we can see that the enzyme is electrochemically active, so we can have a difference in reading with no analyte, mean no blue here, or with analyte with this blue here. So these are all strategies, means that you have to think about it. When we do research on this sensor, we have to think about how it will give signal. Okay, so we need to understand the principle first, and then we strategize on how to get the signal. And it has to be chemically, not to the chemistry must be correct. Okay, the chemistry must be foolproof. Okay. So this one I don't want to talk about because I will invite somebody talk about enzyme-based biosensor. So I just skip this, right? All right. Okay, so this one. Okay. Okay, question. I think I didn't stop this. Question? Is it too hard for you? Everybody? Are you there?
Yes, Prof. Yes, Prof. We are here.
Yes, yes, doctor.
Yeah, I know this is something foreign, especially for you, Pavitra. You just joined.
Yes, doctor.
Okay. So I think it's okay. So go back and try to read more. Okay. It's not for you to again, this is additional knowledge to you. Okay. Don't worry about final exam. Okay. You don't have to memorize all this, but at least you understand the principle. Yeah. And starting next week, I think we have to talk about assignment. Yeah. We already have the groups. Yeah. I think Pavitra can just join any groups. Yeah. But we need to discuss on the assignment starting next week. Next week is already week 5. Yeah. I'm sure you also have another assignment, other assignment from other subjects as well. Okay. All right. I think we
Okay, Prof.
Okay, doctor.
all right.
Thank you.
Bye-bye.
All right, bye, Prof. Thank you.
Thank you, Prof.
Thank you, doctor.